Okay, I had a bit of a technical error, just had to restart the video. Okay, so let's continue. Where did we stop? Okay, so I'm thinking of this EX and EY, and I want to get the angle at which EX the electric field E operates. Okay, so EX is positive, so it lies, from there to there somewhere, from there to there. Well, exactly from there to there. And EY is negative, so it is there, so E will be somewhere around there, more or less. Okay, so I'm going to draw that triangle. Okay, so it's actually upside down, so it's like that. There I've got the one distance, 3.166, and there I've got the other one, 1.828. Oh, you can look at this part, it's not necessary. Okay. So again, just be sure you understand what I'm doing right now. I'm at the origin. I know my X component is somewhere around here. I know my Y component is negative. So I know the EY vector is around there. So the actual E is there. So now I'm after this angle, or this one, either one. Let's say, let's calculate that one. So that's the angle at this little triangle I redrew here. Let's say that angle is alpha that I want. So then I know that tan of alpha is opposite over adjacent. We want to add over 3.166. Leave space again. So alpha is equal to tan inverse of that. Okay, squish. Okay, at least don't answer like this. But make it clear what you're doing. Okay, so tan inverse of 1.828 divided by 3.166. Okay, pretty much 30 degrees. Oh yeah, that's not surprising that it's 30 degrees. It should actually be exactly 30 degrees. So this is interesting. If you were to calculate this, that should work out as exactly 30 degrees. So what are all of these digits there? That shouldn't be there. Those are the results of round-off errors that we made here and here. We had to round them off, but because we did, we've got that to thank for it. Those are errors. Those are errors due to working with inexact numbers. Now you can reason just geometrically that that angle must be 30 degrees. I suppose I can quickly talk about that at the end, but for now we solve this a conventional way. Okay, so that alpha is 30 degrees. So I see that this angle here is 30 degrees. So how am I going to answer what E is then, in other words? So I'm going to say E is equal to 3.7 times 10 to the 7 newtons per coulomb. Right. At what angle? At what angle? I have to provide the angle. This is not a scalar. What's with the nearest scalar? The direction is missing. Now if I just want to provide a single degree answer, then it has to be clockwise. Anti-clockwise from the x direction. Anti-clockwise from the x direction. What would that be? 90 plus 90 plus 90, that's 270. 270 till here. And then that distance is 30, so that distance is 60, so it is 330 degrees to here. So I can say this is at 330 degrees, and that would suffice. Otherwise, you could say you worked out that as 30 degrees. Otherwise, you would have to say E is equal to 3.7 times 10 to the 7 newtons per coulomb at 30 degrees clockwise to positive x-axis. Right, again, if you just provide the degrees, then the convention is that it is anti-clockwise from the positive x-axis. Okay, how did I know that must be 30 degrees? Well, I knew that because the situation, I've got one vector here of a certain length L at a 30 degree angle, and another one here of the same length L, and I'm adding them together. So I was just thinking in terms of the parallelogram law, what happens when you add them. So there's going to be the resulting vector, because this is L and this is L, so this is also L and this is also L, so these angles are all the same. And from there I see that this must also be exactly 30. All these must be, no, this must be 60 degrees and 30 degrees, right? Yeah, no. So just thinking of it in terms of it in these terms, you can see that this angle must be exactly 30 degrees. So that it's very interesting to see it illustrated this way. Everything apart from the 30 are due to the round of errors that we made. So that is very interesting. Okay, and that's it for question 5.